Hey guys, welcome back to the channel. This is the third lesson on impulse and momentum. Yes, it is going to be the last lesson as well. In this lesson, we'll be talking about collision. We'll be understanding all the aspects of collision. It is an important application of conservation of momentum. We have already covered different units on this channel as per the honors physics curriculum. Whether you are an honors physics student or an AP physics student, this channel is equally worth it for you. Whenever we are learning something new, it takes time to understand. So, in order to understand the value of these concepts, do check these videos out for a few minutes and let's get started.
Apart from this, in today's class, we'll talk about collision. So, what is collision and what are the different types of collision we do observe? We'll talk about it as well as we'll see that what forms of energy is being conserved and what forms of energy are not conserved. What are the specific case when the collision might happen and that will create no loss in energy? We'll talk about all the possible aspects. So, collision means when two bodies collide with each other in such a way that their energies, or you can say their kinetic energies, are redistributed. Like, for example, suppose there were two objects, they were moving towards each other, I would say. After the collision, what happens here is that the two bodies which are moving with initial velocity, they changed their velocities. Or you can say they changed their velocities in terms of magnitude as well as in terms of direction. Like, for example, there were two bodies, one is having mass of 2 kg, another is having the same mass as 2 kg. It is moving with 10 meters per second and it is moving with 5 meters per second. So what happens here is that after the collision, this 2 kg mass is going in this direction with 5 meters per second, whereas this 2 kg mass is going in this direction with, guess what, 10 meters per second of velocity. And why this change is observed? Because the mass is the same, and this thing is something which is generally observed in elastic collision. So elastic collision is the easiest type of collision to understand, in which the net force acting on the system must be zero. And we know that, we know this thing's application. If the net force acting on a system is zero, it means there is no acceleration of the system. And if there is no acceleration, it means momentum is supposed to be conserved. So what does it mean? What does it mean that momentum is conserved? It means that whatever momentum the body possesses initially must be equals to the momentum possessed by the body finally. So initial momentum must be equals to mass times initial velocity of first mass, mass times initial velocity of second mass, moving in the opposite directions. We have to consider the direction of velocity as well here, because velocity is a vector quantity, so we have to consider the direction. Similarly, this thing must be equals to the momentum times velocity of the final velocity of the first object plus mass times velocity of the final second object. So that is the equation which we can use here. Apart from this, elastic collision has one more characteristic, and that characteristic is known as that energy is also conserved in elastic collision. Energy is conserved means initial total energy must be equals to final total energy. And as both the objects are moving in the horizontal direction, the energy they will possess, it is always going to be kinetic energy. So kinetic energy initial must be equals to kinetic energy final. There must not be any final potential or initial potential energy, because the motion or the position above the surface with which they are moving, it must be constant. It must not be changing. So kinetic energy is going to be the constant here. So initial kinetic energy can be written as half mv initial of first particle square plus half times mv initial of second particle square. This thing must be equals to half mv final of first particle square plus half mv initial of, sorry, v final of second particle square. So this is the another equation which we might be using to solve problems. So From this particular section, or you can say this particular type of collision, we got two equations. One, the first equation is equation of momentum, conservation of equation of momentum, and the second equation is conservation of energy, which is specifically kinetic energy. One important thing that we have to talk about is the ratios of velocity after collision and before collision. So let me just assume that initially the particles were moving with some velocity v initial 1 and v initial 2 in the same direction. Now, in order for collision to take place, m initial 1 must be greater than, sorry, v initial 1 must be greater than v initial 2. That is the only case when collision can happen. If the velocity of the object moving in the forward direction is more and the object in the backward in the behind position is less, then there is no possible scenario where they can collide. But if the velocity of the particle which is at, or you can say behind the first one, if it has more velocity, then it might be possible that it will hit it from behind, just like the car does in some cases. So what will happen here is when they collide during collision, the first mass will imply force in the forward direction, whereas the second mass will also imply force in the backward direction, because every force has equal and opposite reaction. So force on 2 due to 1 will be acting in the forward direction, whereas force on 1 due to 2 will be acting in backward direction. And that forces must be equal in terms of magnitude. That's why they will be referred as action reaction pairs. So that is again an important part. So F12 must be equals to F21, and they must be written like that. So this thing also proves Newton's second law, or you can say Newton's third law. So Newton's third law says every action has an equal and opposite reaction. So we can see it here as well. Now, after the collision, what we are going to observe? After collision, we will observe that finally also this velocity, this particle will have some final velocity in the forward direction, and this particle will have some final velocity in forward direction as well. Again, keeping the mass as same constant, but there is no change in the mass. Now, after the collision, we obviously know that V final 2 will be greater than V final 1. Otherwise, the collision doesn't make any sense. So this situation before collision, this solution, this situation at collision, and this situation after a collision. So all the scenarios which are taking place here, we need to keep in mind. Now, there is one important factor that we have to define here, is which is known as coefficient of restitution. Coefficient of restitution is defined by E. It is equals to ratio of speed, or you can say relative velocity of separation, relative velocity of separation over relative velocity of approach. So this is the coefficient of restitution thing. Now, if you just apply this thing in this particular case, so E will be written as, observe it carefully, what is the relative velocity of separation? So relative velocity of separation, with what velocity they are separating with each other. So they must be separating with velocity Vf2 minus Vf1. Whereas what is the relative velocity of approach? With what velocity they are approaching? It is going to be Vi1 minus Vi2. So this is the another case, or you can say another parameter of judging a type of collision.
Right.
For elastic collisions, this coefficient of restitution must be 1. So for elastic collision, you can say this E must be equals to 1. So M, or I should write it as V final 2 minus V final 1 divided by V initial 1 minus V initial 2 must be equals to 1. It simply says that final velocity difference must be equals to initial velocity difference in terms of magnitude of the torque, or velocity of separation must be equals to velocity of approach. So this is the case specifically limited to, you know, elastic collision only. Whereas for another kind of collisions, this is not the case. But yes, what we can say here is that this thing must be applicable in another forms of collision as well. For other type of collision, which is generally called super or inelastic collision, E is not equals to 1. E must lie between 0 and 1. This is for elastic collision case. It means whatever value is given here in the question for inelastic collision, we will use that value of E to form another equation from here. Whatever value is given, we'll put in place of 1. We'll solve the equation. We'll do and find out velocity of, of any object after the collision or before the collision. So what you have to understand here is that this is everything we have to do.
Okay.
Just share your, you can say, screen. We'll do some problem from book directly, because this is the only thing that you have to understand here. For elastic collision, potential kinetic energy is conserved. For elastic collision, momentum is conserved. For elastic collision, we know that coefficient of restitution value should be 1. But whereas for inelastic collision, kinetic energy is not going to be conserved.
Okay.
Momentum is conserved, but not kinetic energy. So apart from this, we will use these two situations as well to find out any problem or solution. So now just do one thing, share your screen
Yeah.
and show me some questions. Let us solve some questions from the book directly now based upon this collision factor.
Yeah.